August 1914. A Belgian soldier stands in a fortification at Liège, watching German infantry probe defensive positions 3 kilometers away. The fortress is protected by reinforced concrete walls 2.5 meters thick, designed to withstand any artillery the Germans could transport to the battlefield. At 0620 hours, a sound unlike any artillery fire previously experienced rolls across the landscape. It is not the sharp crack of field guns, but a deep, sustained roar that resonates in the chest. 7 seconds later, a shell weighing 810 kilograms strikes the fortress roof. The impact creates a pressure wave so violent that men standing 50 meters from the detonation point are killed instantly without visible wounds. The explosion excavates a crater 9 meters across. The concrete casing ruptures. Secondary detonations begin as ammunition stores ignite. Within 40 seconds, the fortress that was designed to hold for weeks is combat ineffective. The weapon that fired that shell was a 420mm howitzer built by Krupp, and the shells it delivered did not merely destroy fortifications through explosive force. They created localized atmospheric disturbances so severe that observers reported sudden winds, pressure-induced deafness, and rain forming spontaneously above impact sites. This was not a metaphor. This was physics. The German army in 1914 faced a siege warfare problem that was architectural and temporal. The Schlieffen Plan required rapid movement through Belgium into France, but Belgian fortresses blocked key routes. These fortifications, constructed beginning in the 1880s, used reinforced concrete technology that made them resistant to contemporary field artillery. The largest German field guns, 210mm howitzers, could damage, but not reliably destroy such structures. Siege artillery capable of breaching the fortifications existed, but required weeks to emplace and operate, time the German offensive plan could not afford. What military planners needed was mobile siege artillery that could be transported by rail, assembled within days, and deliver explosive force sufficient to collapse reinforced concrete structures designed to withstand conventional bombardment. The specification demanded a shell large enough to carry a massive explosive payload, fired at sufficient velocity to penetrate earthwork and concrete before detonating. Standard artillery propellants and barrel designs could not generate the required energy without destroying the gun through excessive chamber pressure. The solution involved a howitzer rather than a gun, firing at high elevation angles to allow gravity to contribute to terminal velocity, and using a barrel reinforced by multiple steel hoops shrunk onto the core tube. The resulting weapon was designated Mercer 14, though it became universally known as Big Bertha, a nickname that obscured its technical sophistication. The weapon consisted of a 420mm smooth-bore barrel, 5 meters long, mounted on a complex carriage that allowed elevation from 40 to 75 degrees. Total weight in firing configuration was approximately 43 tons. Transportation required disassembly into 5 loads, each carried on specialized railway cars. Assembly at the firing position required approximately 6 hours with a trained crew of 200 men and several cranes. The barrel's rifling was minimal, providing just enough spin for stable flight without excessive stress on the shell casing. The breech mechanism was a massive, interrupted screw design capable of sealing against chamber pressures approaching 2,500 atmospheres. The entire system was designed for minimal lifespan. Each gun was expected to fire approximately 50 rounds before requiring barrel replacement due to erosion and stress fractures. The shell itself was the weapon's defining component. It weighed 810 kilograms, of which approximately 110 kilograms was high explosive, typically a mixture of TNT and ammonium nitrate. The shell body was forged steel, thick enough to survive launch acceleration of approximately 2,000 g-forces and subsequent impact with earth or concrete before detonating. The nose fuse was a delayed action design that allowed penetration before detonation, maximizing structural damage. The shell's diameter of 420 millimeters and its weight created aerodynamic properties unlike those of smaller artillery. The projectile's mass meant it retained velocity better than lighter shells, and its size created substantial displacement of air during flight. Muzzle velocity was approximately 425 meters per second. The maximum range was roughly 12 kilometers at optimal elevation. Flight time to maximum range was approximately 30 seconds. During this flight, the shell's passage displaced approximately 50 cubic meters of air per second of travel, creating a temporary low-pressure wake that could be observed as a visible disturbance in humid conditions. The detonation effects were what generated reports of weather manipulation. When 110 kilograms of high explosive detonated, the chemical reaction converted solid material into gas at temperatures exceeding 3,000 degrees Celsius. This gas expanded at supersonic speeds, creating an overpressure wave that propagated outward from the detonation point. Peak overpressure at 5 meters from the blast center exceeded 20 atmospheres, sufficient to cause lethal injuries through pressure alone without requiring fragmentation wounds. At 50 meters, overpressure remained sufficient to rupture eardrums and cause internal injuries. The rapid pressure change also created localized wind as air rushed to fill the low-pressure zone following the blast wave. These winds could reach velocities of 50 meters per second at close range, sufficient to knock men off their feet and scatter loose materials violently. The atmospheric effects extended beyond immediate blast dynamics. The massive explosion heated the surrounding air rapidly, causing it to rise in a convection column. If humidity was sufficient, this rising air cooled as it gained altitude, causing water vapor to condense into visible cloud formations directly above the impact site. Multiple detonations in sequence could create sustained updrafts that generate precipitation. German artillery observers documented cases where bombardments created rain showers over target areas where no precipitation had been forecasted. This was not weather manipulation in the sense of deliberate control, but rather an incidental consequence of releasing enormous thermal energy into the lower atmosphere. The phenomenon required specific humidity and temperature conditions and was not reliably reproducible. Operational deployment began in August 1914 with the assault on Liège. 5 Big Bertha batteries were transported by rail to positions surrounding the fortress belt. Firing commenced on August 12. The psychological impact on Belgian defenders was immediate. The shells arrived with minimal warning, the only precursor being the distant thunder of the guns firing. The detonations were unlike anything troops had experienced. Men reported feeling the blast through the ground before hearing it, as seismic shockwaves traveled faster than sound through rock and soil. The pressure waves caused disorientation and nosebleeds even among personnel in undamaged sections of fortifications. Within 4 days, the fortress complex that was expected to hold for weeks had surrendered or been abandoned. The weapon's effectiveness was replicated at subsequent fortress systems, including Namur, Maubeuge, and Antwerp. Each bombardment followed similar patterns: initial ranging shots, then systematic destruction of specific fortress components, then assault by infantry once defenses were compromised. The Big Bertha shells created effects that conventional siege artillery could not match. Where 210mm shells might require dozens of impacts to collapse a concrete casement, a single 420mm shell could achieve the same result. The time compression this allowed was strategically significant. Fortresses that would have required weeks to reduce with conventional methods fell in days. Comparison with French and Austrian siege artillery reveals Big Bertha's unique characteristics. French forces deployed 370mm mortars that were more mobile but delivered shells weighing only 400 kilograms with proportionally less explosive content. Austrian 305mm howitzers, while effective, required longer emplacement times and achieved shorter ranges. No other combatant fielded mobile siege artillery approaching the 420mm class until later in the war. The Big Bertha represented a singular engineering achievement, though at substantial cost. The limitations were severe. The weapon's size made it vulnerable to counter-battery fire once located. Moving it required extensive railway infrastructure and was slow enough that strategic flexibility was minimal. The 50-round barrel life meant each gun had limited utility before requiring replacement barrels that were expensive and time-consuming to manufacture. Most critically, the weapon was effective only against static fortifications. Once mobile warfare resumed, the Big Bertha's tactical utility declined dramatically. The guns were too heavy for field deployment and required prepared positions. By late 1914, most had been withdrawn to garrison service or storage. Production was limited. Approximately 12 complete weapons were manufactured between 1914 and 1918. Barrel production continued throughout the war to replace worn units, but the weapons themselves saw declining use after 1914. Several were deployed during the Siege of Verdun in 1916, but their impact was less decisive against the extensive field fortifications there. The weapon's reputation exceeded its actual strategic contribution. The psychological effect of the initial Belgian bombardments created a legend that the technical reality could not sustain across 4 years of industrialized warfare. Post-war analysis suggested that Big Bertha's greatest impact was temporal rather than material. By reducing fortress reduction time from weeks to days, it allowed the German offensive to maintain momentum through Belgium in August 1914. Whether this was strategically beneficial is debatable, as rapid advance contributed to the logistical failures that stalled German forces at the Marne. The fortifications would eventually have fallen regardless. The Big Bertha simply accelerated the inevitable while creating a spectacle that obscured the grinding arithmetic of siege warfare. The Belgian soldier at Liège who witnessed the first impact survived the war. His account, recorded in 1920, describes the shell's arrival as creating instant fog from condensed water vapor, followed by winds strong enough to tear equipment from mounting points, followed by structural collapse that seemed to occur in slow motion as pressure waves fractured concrete in progressive layers. He never mentioned the explosion itself. His memory stopped at the pressure wave's arrival and resumed when he regained consciousness buried under rubble. The 810-kilogram shell that struck his fortress created effects that his vocabulary could not adequately describe, effects that observers interpreted as weather because they lacked alternative frameworks for understanding overpressure dynamics at that scale. The weather was mechanical, not meteorological, but the distinction meant nothing to those experiencing it.